Hello, my name is Sai Ravella and I direct the Earth Signals and Systems Group in the Earth Atmospheric and Planetary Sciences Department at MIT. We are very excited to have you with us here today. We have several projects connected by the common themes of using machine learning that's been advanced and optimized using physics to accelerate the assessment of climate risk and the development of climate solutions. We are engaged in the lab, in the field, in computation and methodology, and have, as these images show, been motivated by the exacerbating impacts on lives and livelihood. The images you see here depict the damaging impacts from tropical cyclones in Bangladesh. We are interested in both the tropics and extratropics, particularly Boston, Florida, Puerto Rico, and Cape Town, as part of the MIT Climate Grand Challenges projects. The problem of assessing risk is complicated, at least in part due to coupling between the hazards and their compound impacts. Tropical cyclones, for example, originate in all major basins and bring with them extreme winds, produce rainfall, which induce storm surges that couple with waves, tides, and sea level rise, which includes a local component due to land surface changes. Rainfall produces additional inland inundation that further requires considering river levels, snowmelt, sedimentation, and morphodynamics. Assessing risk, which involves quantifying the hazard, vulnerability, and exposure, is no easy task, but must often form the basis, especially if it is to be an informed one, for climate solutions. We explore the use of machine learning to accelerate the propagation of uncertainty and information through these hazard chains to bring efficacy to the risk assessment process. If we could quantify risk effectively, despite a large number of coupled processes and their uncertain parameters, we can devise solutions cognizant of future risk, implementing and revising them as time marches on. For example, quantifying the coastal flood risk at Tampa, as shown in these images, can enable decisions such as elevating, armoring, or abandoning land, and including or removing various constituents, such as dynamic ice sheet melting. We are somewhat well equipped to deal with the more regular exacerbation of extremes in developing these solutions. We are, however, quite ill equipped to deal with irregular changes such as tipping points. Our group also leverages machine learning to solve both type of problems, one where there is a gradual and predictable change, and another where there are sudden critical failures or the onset of tipping points. We are a methodologically focused group that looks at the entire cycle of risk assessment and decision programming across a range of hazards. Our world includes a consideration of the past, present, near future, and distant future, where we imagine risk increases. To build climate solutions, we first consider decision variables such as losses, poverty, productivity, or any number of socioeconomic variables. Projecting these variables directly into the distant future is rather difficult. Note that physics exists in many cases. Success has only been found at short horizons. So, what are we to do? In the present day, we map these variables and build relationships with physical models. And this mapping is obviously done in a data driven manner. Often, the mapping must be done at very high resolution to capture local and regional effects. But projecting the high resolution assimilated climate models to the distant future is rather expensive. Thus, we resort to lower resolution or reduced models, simulating them to quantify uncertainty and search for extreme scenarios. But the catch is that the reduction entails a loss of detail, which we must reconstruct through a process of downscaling for both the physical and decision variables. Downscale projections enable the estimation of risk with some efficacy that, given sustainability objectives, lead to decision problems that must be solved to advance risk-informed climate solutions. Having gone forward and backward, and by the way, this is a very classic system science paradigm, we can implement the action step ready for the next cycle. I hope you can see that this entire process is very amenable to the use of machine learning solutions in the process of model reduction, in the process of uncertainty quantification, for the search for extremes, for downscaling, and for solving decision problems. Much of the work in my group is the result of my advisor, Kerry Emanuel, and his untiring efforts in bringing physics to climate risk. My group has several postdocs, graduate and undergraduate students working on projects combining physics with machine learning across the entire spectrum of Earth, planets, climate, and life applications that are found throughout our department. Today, you will hear from four of us in presentations and demonstrations in adjoining stations on this table, including downscaling and geothermal climate solutions. I hope you enjoy them, and we would love to get your feedback. Thank you.